So, yesterday we started at the end trying to describe what we are supposed to do today is to look at problems which are actually non-convex in nature, but they can be tackled by using the properties of convex functions, because if you observe this fact that for example, this minimization of the difference of two convex function over say x element of R n, then you will have observed that here we have two convex functions. So, you can use some properties about convexity, and we are also talking about the maximization of a convex function, which we have showed to be actually a non-convex problem. So, if you look at, so we have basically two problems, minimization of f x minus g x, for the time being let it be over x element of R n, and the maximization of f x x element of c. In the previous problem, in the problem I would call maybe I should say two things. Let me call this as P 1, this is what we are going to discuss in the beginning, and this let me call as P 2, because we will discuss this the next. Observe that from P 1 can follow from P 2, because in P 1 if f is 0 throughout, then it is nothing but minimization of a concave function, because it is minus g x, so it is maximization of a convex function. So, now let us go to this problem of maximization of a convex function. We have shown yesterday by an example, very simple drawing, that a local maxima of a convex function, which is minus 1 in this case. I will just redraw it, make it look nicer. So, if it is which was minus 1 in this case, is not the global maximum, which is plus 1 in the case when I am restricting C over minus 1 and plus 1. So, this is something which is very important to realize. And then see, since even problem P 1 can be posed as a problem P 2 by writing this as mean of minus of f x and then writing phi x minus f x, where phi x is 0. So, these two problems are very strongly related, or rather interchangeable in some sense. Now, how would we do anything about them? Okay, let us maybe you are tempted to think about P 2 first, because we have already thought about minimization. So, just taking again a little bit of detour and listening to the dictates of maybe your heart and my heart too, I would like to just show how do I find the optimality condition for this problem. Now, let us be very clear that the optimality condition that I find for this problem is essentially a necessary condition and not a sufficient one, because this is a non-convex problem. So, you cannot expect optimality condition to be both necessary and sufficient. So, let x bar be a mean of P 2. Let me call it local mean, that is better, be a local mean of P 2. This implies that for V element of R n, there exists lambda greater than 0 sufficiently small such that f of x plus x bar plus lambda v minus g of x bar plus lambda v is greater than equal to f of x bar minus g of x bar. This would immediately bring to the fore the following fact. Now, dividing my lambda on both sides, because lambda is sufficiently small, and taking the limit as lambda tends to 0. Now, both these limits exist because these are convex functions. So, see, we have now transferred our difficulty of non-convexity to the efficiency of convexity. Here would immediately imply and this would be true for all V. Because this V was chosen to be arbitrary. So, since V was arbitrary, now if you look at this kind of thing, this is also an optimality condition, but in the minimality form. But this would, but you see from here you cannot go back to this, you cannot show that x bar is a local minimum, impossible. Now, what would this imply? Can I transfer it into a subdifferential condition? Of course, for any xi element of del g x bar, it would imply that g dash x bar v is greater than equal to xi v for all v element of Rn. So, this would imply that xi is element, because of this condition xi is also element of del of f of x bar, which simply implies that del g of x bar is actually a subset of del f of x bar. So, this is the subdifferential based optimality condition for the problem P 2. So, resisting further temptations, we will just look into this slightly more bothersome looking problem, a maximization one. Maybe our habit has become so over this 38 or 35, 37 or 38 lectures that we are seeing, that we are always talking about minimization and there is nothing like about maximization, and so things are very different. Now, how do we write down an optimality condition for a maxima? Now, suppose x bar is a global maximum, is a global maximum for P, it is a global maximum for P 1. Then for all x in C, f of x is bigger than f of x bar, and that would imply that f of x minus f of x bar is bigger than, sorry, I am making a mistake, it is maximum. So, it will be opposite. So, it will imply that f of x minus f of x bar is negative. So, now again applying the definition of the subgradient, for all x element of C and for all xi element of the normal cone to C at x bar. This would simply imply that del of f x bar is n C x bar, is in a subset of the normal cone to C at x bar. So, this is the condition for x bar to be a necessary condition for x bar to be a global maximum of a convex function. Note that this is a necessary condition and not sufficient. I will show you an example which will tell you that this example is from a paper of mine which was published in 2006, which dealt with this problem of maximization for convex and non-convex problems. So, and the study of their optimality conditions. So, if you look at here, if you look at this thing now, consider this problem max of this, which is a convex function. I want to maximize this, x is in R, and my problem now is to max this f x over x element of minus 1 0, which is my C. So, I am showing that I will show a point where this condition would be satisfied, but that point will not be a global maximizer. So, let x bar equal to 0. So, N C 0 is a set of all x such that x is greater than or equal to 0. You figure it out how? Figure out. You have to figure out how I have done this. I will leave it to you, but it is very simple because it is on the real line. It is very simple to see. You just have to apply the notion of projection. Now, if you calculate the subdifferential at 0, the subdifferential at 0 is on one side it is x square, other side it is x. So, it is 0 1. This also I leave it out to figure out. I do not do this, and I put both of these together as a homework. And if you look at this, then it is clear that del f of 0 but if you look at the graph of this function, this is my y equal to x, and here between the positive part and then it goes till 1 and goes up x square. So, the graph of the function is not really like this. The graph of the function looks here and then it goes up again. So, here if you look at this point, x equal to 0 is a local, is a global minimizer. Here x equal to 0, this is the graph, and x equal to 0 over the set 0 minus 1, sorry minus 1 0, and take x equal to 0 and take x equal to minus 1. So, on this particular set it is clear that 0 is the global minimizer of the function. So, you can actually over the whole R it is a global minimizer. So, you can really see that this condition is satisfied, but x equal to 0 is a global minimizer. So, this example appeared in, I will just take a second to tell you. The example appeared in a paper by myself, which says, with the title Optimality Condition conditions for maximizing locally Lipschitz functions. It is published in a journal Optimization in volume 54, pages 377 to 389 in 2005, sorry not 2006, 2005. Okay. So, for getting this, let us look at some result due to Strzekalowski, which says the following. Okay, let us tell you something which is much more interesting. So, we will now we will now show a result or mention a result by Rockefeller. It is from the book Convex Analysis by Rockefeller. There is a chapter on maximization of convex functions. So, the result says the following. That a convex function will never attain its minimum, local or global, whatever it is, relative to the set C, which is a closed convex set. It will never attain its local or global minimum in the interior. It will be always in the boundary. If not, that function will become constant. So, here is the major result. So, I will write it as theorem 1. Consider a function f from R n to R and a convex set C subset of R n that is polyhedral, sorry not I said closed set, it should be polyhedral. So, this is a reason, for example, here in the first example this set -1 to +1 is a polyhedral set, and that is why for linear programming problem you always have the solutions on the boundary. The linear function is both convex and concave. Convex set which is polyhedral, suppose that there are no half lines in C on which f is unbounded below. This is a very important result. Then f attains its supremum over C. So, it is a condition under which the supremum is achieved. So, basically you can find the point of maxima of a convex function on a polyhedral set if this condition holds. Another result which is also from Rockefeller is the following. These are very fundamental results about maximization of convex functions, is that if you have a convex function on a convex set and if attains a point in the interior, then the function must be constant. So, let f be R n to R n a convex function and C be a convex set such that interior of C or int of C is not equal to phi. If f attains its supremum or the maximum value, whichever you want to call it, relative to C at some point could be a local minimum also. In the interior of C, then f is constant. Basically, you cannot have a scenario like this. Suppose you have a set like this and you have convex function you are minimizing, and you say okay, let the convex function is having something having a local maxima here, and then of course, the function has to come down something like this and a global maxima here. See, even if it cannot have a local minima, once it has a local maxima, you see just for a function from R to R, the function has to rise on one side, drop on another side. Once you do that, you lose the convexity of the epigraph, and hence the function would not remain to be convex. So, if the function is convex, it cannot attain its supremum relative to C in the interior of C if the C has an interior. So, that is a very, very important conclusion, and this conclusion should be always kept in mind. Now, of course, you can ask that can you improve this condition in some way, so that our problem, our condition becomes both necessary and sufficient, that is, can you guarantee a necessary and sufficient condition for local minima. We can do something, but there are many research steps here, but we are not going to go through any of these research steps, but what we are going to do is we are going to try to mention the major result that is essentially due to Hiria, Turuti and Ledaev, and a different proof was provided by myself in that paper which I had mentioned, when a different approach was taken, and it was done for a certain different class of functions, not exactly convex, but some slightly generalized version of a convex function. So, let me mention this result due to Hiria, Turuti and Ledaev. So, I will also, this is a paper which they published long back in, so both of them are leading optimizers, and those who really love mathematics and want to become convex analysts or mathematical optimizers should read papers by Hiria, Turuti and his books. So, again give me a second, so that I will let you know exactly what is the details of the paper. So, this paper, the title is a note on the characterization of a global maxima of a you do not have to bother much. This is only for people who want to go and read these papers. See, when a course like this, which is quite important for application, but also mathematically very interesting, is done, at the end we should give in some research flavors. It is not just some course material done so that you pass exams. There should be some courses in this NPTEL category which would also give you some sort of research flavors. I think most courses would give you some sort of research flavor. So, that is very important. So, at the end of this course we are trying to give you some research flavor, and that is why we have started mentioning papers here rather than just giving names of books. Convex function over a convex set. Now, this paper was published in Journal of Convex Analysis. In volume 3. So, every journal has a volume, and every volume has some numbers, and then papers are published in each of these numbers on a particular volume. So, I am not writing the numbers, but just the volume, because that is the traditional way to write. So, pages 55 to 61, and it was published in 1996. So, my paper was published almost 10 years later, but dealt with slightly different things. So, The theorem is as follows. Of course, I will try to show you how to prove this result, and that could be an interesting way to end our discussion for today. So, consider a convex function f from Rn to R and a closed convex function and a closed convex set let x bar be such okay. This is what I have, that the infimum there is an, let x bar be such that it is strictly bigger than the infimum. Of course, if I am trying to pose it as a candidate of maximum, as a the guy where the maximum is achieved, then this should at least be true, right. Then x bar element of C is a maximizer. I am now talking about a global maximizer, because I want to get a global maximization condition. That is very, very important, because at the end I want a global maximizer. I will go back and again put a homework on you. I am giving too many homeworks. So, if I have if x bar was a local maxima, can you devise an optimality condition? Sorry, but try it out. It will be fun. Those who do not want to listen to all these things, as I am talking about flavors of research, and you feel that you have got some idea of certain things which you can apply in your work, you may just hang around and see something, and it may not even bother to concentrate much, but it is not harmful to have a look at things. C is a maximizer, is a global maximum of f over C if and only if. So, now it is a necessary and sufficient condition, del of f x. Now, the condition would look quite tough, but there is no other way, it seems, for all x element of C satisfying, if x bar is the only point which satisfies this, then also this will be true. So, what it says, if there is only one x for which f x equal to f x bar, and there is no other x other than x bar, then also if we have del f x bar element subset of n c x bar, then also f x bar would be strictly greater than f x bar would be true. Then if this condition is satisfied and x bar is the only point for which this is holding true, and there is no other x for in C for which f x is equal to f x bar, then also we will get x bar as a global maximizer. If you look back, you will try to see this condition that x equal to 0 does not satisfy this basic result, sorry, this basic condition required. So, this is important, this condition is fundamental. So, now maybe I will start doing the way I had proved it. So, I will go through the proof step by step. In mathematical courses, it is quite instructional to go through the proofs. So, with this proof, I will be possibly ending today's talk. and come to minimization of DC functions tomorrow. Now, you have observed in the statement that this question statement says it is if and only if. So, it is necessary and sufficient. So, if x bar is a global minimizer, of course, this condition is obviously true, right, unless the function is constant, this is obviously true. Then what we have already proved that del of f x bar is subset of n c x bar. So, if f x is equal to f x bar, then for all such x, we will have, of course, x is in C, x is in C. See, f x is equal to f x bar does not mean that f x is equal to f x bar does not mean that x is equal to x bar. So, what we have said that now if f x is equal to f x bar, so basically if I have f y minus f x bar, so now x bar is a global minimizer. So, this is what I have to show. So, what I will do is that okay, so f I minus f x bar must be less than or equal to 0 for all y element of C. So, f I is less than or equal to f x, I have replaced f x bar with f x, whenever x is equal to f x bar, this is true. Then again repeat the same sort of argument I would have had with f x bar, and then you get this simple proof. This is, I could have left it as homework, but okay. So, now we have to look at the converse part. So, again we will use one of the biggest weapons of proving things in mathematics, which is called proof by contradiction. So, which in this case we will assume that, let assume on the contrary that x bar is not a global maximizer. F on C, which means there exists x hat element of C such that f of x hat is strictly bigger than f x. Now, sorry, f of x bar. Consider the following level set. S level set. So, you can also write it as level f x bar whatever, but I am just writing in this simple form. This is usually many research papers, they would use this sort of symbol rather than the lev of something. So, the level set is a set of all x element of C here, because we are only restricted to us over C. So, one thing is clear that x hat is not an element of S x bar. Since f is convex, S x bar is a convex set. I am sure you remember this very important statement, but a statement which you have mentioned long back in the very beginning of the course. If you are not sure, convince yourself. So, now once this is done, let us see how much, at what distance is x hat from this level set, right. See, these are all the values of f x. So, why I am doing this, that is the whole question. So, I know that, so these are all the values of x which are below f x bar. Now, I really want to find the distance of x hat from x bar. So, the maximizer is definitely outside S x bar. X hat could be also the maximizer, it may not be the maximizer, something I do not know. So, it is very important that it is important for us to know that okay, of course, the minimizer of the function is lying here, and so x hat could be the maximizer, I have no idea, but x hat actually breaks this, because x bar we have assumed not to be a maximizer. So, it is very important for us to know an estimate of how far is x hat from x bar. Is x hat is also in C, is the distance 0? Here of course, sorry, here we have shown that x hat is in C, but x hat is not in S x bar. So, what is the distance? That is very important, means how far is this point x bar from from the actual minimizer. So, we are trying to estimate that distance. So, in doing so we are trying to estimate, we are trying to solve this projection problem, which you know that I am trying to find the distance of the set, the level set subject to f x is less than equal to f x bar element of C. So, I am trying to solve this convex optimization problem, and this is a strongly convex problem over a closed convex set which has a unique solution. So, this problem, this projection problem. So, basically I am trying to see what is the distance between x set and S x bar, the level set. So, of course, I have f x, the infimum has to be in S x bar, and the infimum is of course strictly if the infimum is achieved, the minimizer has to be in S x bar, and that is strictly less than f x bar. So, it is very important to know at what distance the real maximizer might be, that is what we are going to show. So, we will get into some contradiction when we try to estimate this distance. When we estimate this distance, we will show that some contradiction will arise. So, there cannot be a point outside S x hat. So, if there is x hat is really outside C, we will get a proper estimation of the distance between x hat and C, and we will reach no contradiction. If I reach a contradiction, well, I am trying to see how far is x hat from this particular level set, that is how far the minimizer might be from my x bar. If I reach a contradiction there, then my basic assumption that x bar is not a maximizer is true. So, see the idea is like this, I have assumed that x bar is a maximizer, and now I am trying to, I found a point x hat, there must be a point x hat which would be strictly bigger than f x bar. Now, I am looking at all the values of x such that f x is less than f x bar. Now, x hat is outside it, I am trying, so x hat the minimizer might be somewhere so outside S x bar. So, I am trying to at least estimate the distance between x bar and the set S x bar and x hat. If I am unable to if I make the estimate and run into a contradiction, means x hat could not be outside C, x hat has to be in C, and hence proving that x bar is a maximizer. So, let us try to do this and see if we can run into any contradiction. Now, again you might ask me, how do I start doing this? So, let us assume we will go by using our standard Phrygian optimality condition. To do this, we will apply first the Phrygian conditions. You see, we are not aware whether there is any, I do not know whether Slater condition is holding here. If Slater condition holds, then I can directly apply. If the Slater condition does not hold, then I do not know. So, there exists a minimizer of this problem, say x tilde is a minimizer of the projection problem. Then what would happen is that I will apply the Phrygian condition or the John conditions, whatever you want to say. by Phrygian conditions there would exist lambda naught lambda 1 not equal to 0, lambda naught greater than 0, lambda 1 greater than 0, such that 0 is element of lambda naught x tilde minus x hat plus lambda del f lambda 1 del f x tilde plus n c x tilde. See, the problem is that I cannot immediately talk about Karush-Kuntakar conditions because I do not know whether the Slater condition holds here. If I know that the Slater condition holds here, then it is direct, but here I do not know whether the Slater condition holds, and let us see what we can do further. Now, once we do this, and also it would, this is the first condition and the second condition is the complementary slackness condition, which will say that lambda 1 f x tilde minus f x bar is equal to 0. Assume that lambda naught is equal to 0. Let this would imply that lambda 1 must be strictly bigger than 0. Thus, we have from this expression, the number 2 expression, from 2 f x tilde must be equal to f x bar. Absolutely, it has to be like that, because lambda is strictly bigger than 0, this cannot be strictly less than 0, right. Then it will be strictly less than 0, and from 1 we will simply have the condition lambda 1 del f x tilde plus n c x tilde, 0 belonging to this. So, this would imply, because lambda 1 is positive, I can divide by lambda 1 on both sides and the lambda 1 would be absorbed in the normal cone, because it is a cone. So, 0 would belong to del f x tilde plus n c x tilde. So, this is nothing but a necessary and sufficient condition for a point to be a minimizer of the convex function over C. So, x bar is the point. So, you see how beautifully interestingly we have brought in what we have learned about convex minimization in the study of convex maximization. So, thus x bar is a minimizer of f over C, that is f x bar is inf of f x. But this implies that by our first condition in the result, by this condition will immediately imply the first condition, that f x tilde is strictly less than f x bar, which is a contradiction. So, this would imply a contradiction. Thus, lambda naught is strictly greater than 0. Now, okay, what would happen if lambda 1 is equal to 0, right? Let us now assume lambda 1 is equal to 0. So, because lambda naught is strictly greater than 0, since lambda naught is strictly greater than 0, this would imply that 0 would be contained in this set. This would imply that x hat minus x tilde is element of n c x tilde, which would imply that x hat minus x tilde x hat minus x tilde x hat minus x tilde. So, this would immediately imply that x hat is equal to x tilde, which is a contradiction, because this is in S x bar, sorry, this is not in S x bar and this thing is in S x bar. So, there is a contradiction. So, this would imply for us that lambda 1 is also strictly bigger than 0. That is great. So, what happens? So, there exists a xi element of del f x tilde and eta element of n c x tilde by your first optimality condition. It would imply that 0 must be equal to lambda naught x tilde minus x hat plus lambda 1 xi plus eta. Now, what we have said is that since f x tilde is equal to f x bar, that is what we have got, because lambda 1 is now strictly bigger than 0. So, it has to be, since as so this is now, so I wanted to show lambda 1 strictly greater than 0, because this is what I wanted to show. Now, once I have this would imply that del of f x tilde is subset of n c x tilde. So, this xi that you have is also lying in n c x tilde. So, it would imply that minus lambda 1 does not matter, lambda 1 into xi, x hat minus x tilde would be greater than equal to 0. So, this would be anyway less than equal to 0. So, lambda 1 is positive. So, you take the minus, it will be strictly greater than 0. Okay. Now, again it is simple to see that if I multiply, now what I did was basically I took lambda naught xi on this side, and now if I multiply on both sides, so what I did was lambda 1 xi x hat minus x tilde. Actually, what I did was I took minus lambda hat xi, I wrote this to be x tilde minus x hat plus eta. Okay. Now, I am multiplying x hat minus x tilde. So, what I did was I did multiply this with x hat minus x tilde, and when I multiplied this with lambda naught, it became x tilde minus x hat with x hat minus x tilde plus eta times x hat minus x tilde. Now, this is less than equal to 0, this thing, okay, I have observed that this part is strictly bigger than 0, and now lambda naught into what you would have is this x tilde minus x hat, they cannot be equal, whole square plus eta into x hat tilde minus this. So, this is less than equal to 0, because eta is in the normal cone, and this is strictly less than 0. This is strictly bigger than 0, lambda is strictly positive. So, this is strictly less than 0. So, this whole thing is strictly less than 0. So, this part is strictly greater than 0, and this part becomes strictly less than 0, that runs into a contradiction. So, whatever I have assumed in the beginning, that x bar is not a maximizer, is wrong, and x bar is a global maximizer of the problem. And hence, we end our discussion tomorrow, and we will go today, and we go tomorrow to the discussion of minimization of our DC function over a set C or over the whole R n, whatever is simple for us. Thank you, and hoping that you look back into the thing tomorrow.